Okay, welcome everyone. This is the Q&A part of the second Spotlight presentation session. So welcome everyone. We're gonna open the floor here for you to ask questions to the speakers from these 6 papers. I believe this was a very interesting session of a mixture of nice applications and some theory of these. So please write them down either here on the Zoom chat or on the conference platform. And then we have some of the authors here as well that might be able to answer those questions. So I'll give a couple of seconds for you to start asking the questions. Do we have any of the authors here from the first paper? So either Igor, Sergio, Douglas, or Nubia? See that around. What about the second paper? We have Jerivan, Janderson, Christian, Ramiro, Alberto, or Bruno. Any of those are here? If not, I see Lucas is here. So Lucas, are you the presenter for your paper?
Yes. Hi.
Okay. Hi, Lucas. Yeah, this was a very interesting paper and interesting result. So my question is about the fact that in information theory, the quickest change point detection problem has been studied for many years now. So my question was about performance guarantees of the methods that you're proposing. One of the advantages of traditional approaches of information theoretical approaches is that we have explicit performance guarantees. But once we introduce the reinforcement learning models here, we lose that. So can you talk a little bit about the balance between having very fast algorithms that work in practice versus having good, strong performance guarantees, theoretical performance guarantees?
Thank you a lot for the interest in our work and for the question. So basically, the kind of change point detection algorithm that we use in our paper is a Cousin method. These methods are based on likelihood ratios between different probabilistic distributions. And yes, they have a lot of many theoretical guarantees. The only assumption that we had to make was that the distribution was a Gaussian distribution, or in our case, a multivariate Gaussian distribution. And there's talking about trade-offs, there's a very important trade-off that we had to consider, that is between the false alarm rate and the delay for detection. So this is a main point for trade-offs here. And at one extreme, we can not care about false alarms, and we can detect the changes very fast, but of course we can sometimes make wrong predictions. In the other extreme, we can be very careful about false alarm rates, but as soon as we can guarantee that the change will be detected, even if that delay might be not too low.
Okay, yes, and a follow-up is about the uses of the word like high confidence. Like, it was not clear to me what was your specific definition of high confidence in the context of your problem.
Yeah, so when we say high confidence, is a high confidence relation to the false alarm rate, basically.
Yeah, okay, just to wrap up then, Lincoln, can you share us about like your experience of these specific problems once you start thinking about critical applications like handling control where human lives are in at play when using these methods that might not be so much interpretable based on your work?
I think it's a little bit difficult to answer this without create some hypothesis and proof, but when we start looking to prove my model is doing right and answering the questions correctly, we need to explain this for the audience. Like if I have some expert in the area to regulate this. So I think this is one of the main questions of this work, but it's a little a brief discussion. So we had a lot of open questions here.
I think we're having some connectivity issues, but yeah, I think we can close down the session now and go on to so we don't delay the mentoring part.